In this video, we will finish up our discussion of the calculus of parametric curves by introducing one new formula, the formula for arc length. So if we have a parametric curve given by x equals f of t, y equals g of t for the parameter t in some specific interval. So in this case, we're thinking graphically, we're going from t equals a as our initial point, and we're finishing at t equals b as our terminal points. A common question we could ask is, what is the length of the curve? And what we really mean by this is if we visualize this blue curve as being a piece of string, if we were to take the two ends of the string and to pull them tight, what we could then do is measure the length with a ruler. However, since we can't physically do that, the next best thing might be to have a formula we can use to calculate that arc length. And this is very similar to the formula that we've encountered in Calculus 1 for calculating the arc length of a Cartesian curve. So what we would need to do is find dx dt and dy dt, the derivatives of the two parametric curves, and combine them with this formula. And furthermore, let me observe that because of this square root which is present, some of these arc length integrals can turn out to be quite difficult, so we will be very careful in terms of the examples that we give you to make sure that they will work out in a reasonable fashion. So let's investigate a few examples. To begin, let's find the length of the parametric curve given by x equals cosine, y equals sine from 0 to 2 pi. So the two main ingredients we need here would be dx dt, and the derivative of cosine with respect to t is minus sine t, and dy dt, the derivative of sine with respect to t is cosine of t. Then our arc length formula is that we integrate over how the t value or parameter varies, 0 to 2 pi. So depending upon the interval we're given, the limits of integration would change. And what we integrate is the square root of dx dt squared, so minus sine t, plus cosine t squared, the dy dt. And note that something very nice is happening in this case. Sine squared plus cosine squared is 1. So this is really the ideal case. This becomes the integral from 0 to 2 pi. And I'm going to write an extra step just to make sure we all see this. And this will be sine squared plus cosine squared. Sine squared plus cosine squared is 1, so it's the integral from 0 to 2 pi of 1. And whenever we're integrating a constant, what we need to do is take that constant 1 and we multiply it by the length of the interval. So 2 pi minus 0, so the length of this curve is 2 pi. Now it's worth asking here if we think this is a reasonable solution. Well, if we recall back to a previous video, when we have these parametric equations, x equals cosine, y equals sine, if we're going from 0 to 2 pi, those parametric equations satisfy cosine squared plus sine squared equals 1, that is x squared plus y squared equals 1. So our parametric curve in this case is a circle of radius 1 centered at the origin. And the circumference of this circle is 2 pi r, so just 2 pi. In fact, one could maybe easily observe if we changed this interval from, say, 0 to pi, that would just be the top half of the circle, so its length would be pi. If it was 0 to pi over 2, it would be this upper right-hand quarter, so just pi over 2, and so on. So one additional example using the arc length formula. Let's find the length of the parametric curve given by x equals 2 minus t, y equals 2t minus 3, as the parameter value varies from minus 3 to 3. So the two ingredients we need here, dx dt, which would be minus 1, and dy dt, which is 2. So the length of the curve is the definite integral over how the parameter values vary, minus 3 to 3. And we integrate the square root of dx dt squared plus dy dt squared. So minus 1 squared plus 2 squared is 5. So underneath the square root we have 5, so this is simply the square root of 5, which is a constant, which means it can be pulled in front of the integral. And as we mentioned a moment ago, if we want to integrate a constant over an interval, we just multiply it by the length of the interval. So 3 minus 3, and we end up with the length of the curve being 6 square root of 5.